So I am opening the topic simple harmonic motion. This is a kind of motion in which sine theta, cos theta, these two functions are used. So what is this kind of motion is? This is related to rotation motion, but it is not a rotational motion, it is an oscillatory motion. How? See, suppose a point P is moving on a circle, starting from this position, and it is rotating like this. This point is moving on the circle around the center O. Now, if we draw perpendicular from the point P on the y-axis, suppose this point is known as M, then the point M will also move. For example, when P point was here, then the perpendicular from this very point on the y-axis was here. When the point has moved to this position, the perpendicular has the foot, perpendicular on the y-axis has the foot on point M. As the point P approaches the top of the circle, the M point which goes on moving also reaches this position. Are you getting this? Yes.
Sir, yes.
Now this, as P point goes further, suppose rotation it continues up to this. Now the perpendicular on the y-axis will come back. First, the M point has moved from origin to the topmost point here, suppose T. And now as the point P on the circle moves further, the M point starts coming down. When the point P reaches here, the perpendicular from this point on the y-axis will reach origin. So M point will reach here. As the point P continues rotating, continues moving on the circle further, this point, suppose this is the foot of the perpendicular on y-axis. Now this point M has come down. As the point P reaches the lowest point of the circle, suppose L, then the point M which is moving on the y-axis also reaches the lowest point L. Further, when point P reaches here, the foot of the perpendicular starts coming up again, like this. And when the point P comes back to origin position, the starting position back, the foot of the perpendicular coincides with origin back. So what kind of motion the point M is having? The point M is having the motion of the kind that first it begins from origin, goes up to the topmost point T, then comes down, but does not stop at origin. it goes further down and reaches the lowest point L, and then again comes up and reaches the position origin where from it started. Is this clear? Yes.
Sir, yes.
So this is the way the point M is moving. This is M point. M point is set to be in simple harmonic motion. Now, simple harmonic motion is a to and fro motion or oscillatory motion. It is a specific kind of oscillatory motion. What is the relation of this motion with sine function? Suppose P point, which is moving on the circle, makes an angle theta with the positive direction of x-axis. This is x-axis. Here this is y-axis. Then, and radius is suppose 1. We have taken the radius this time, radius of the circle equal to 1. Now, radius is equal to 1. And if I draw a perpendicular from P on the x-axis, then OM length is equal to, suppose this point is N, then OM is equal to PN. Is it okay? Because here is 90 degree, here y-axis and axis are also having 90 degree. This is also 90. So this fourth angle is also 90. This is a rectangle. So OM distance is equal to PN. Is it right?
Sir, yes.
But when P point is in the first quadrant, then Pn is the coordinate, y coordinate of this point is positive. In the second quadrant also, the y coordinate is positive, and that will be equal to this length. Whatever is the length of OM, the perpendicular has the same value. But when the point P moves to the third quadrant, then the y coordinate becomes negative. Then the y coordinate becomes negative, and this displacement which is we are talking about, OM displacement. As far as the displacement is upwards, we want to take it also as positive, and when the displacement will be downwards, then we want to take it as negative. So we can say that displacement OM can be replaced by displacement Pn, which is y coordinate of the point. So y coordinate upon 1, radius is 1, that is sine theta. Sine theta is y coordinate upon 1. And y coordinate we have taken equal to the displacement OM. So therefore OM is equal to y coordinate of this point. But y coordinate is equal to sine theta. So therefore, if we are talking of this displacement, OM is equal to y coordinate is actually the displacement, and this displacement is equal to sine theta. Is this much clear? Yes, anyone?
Sir, kindly repeat it.
हेलो सर repeat करो.
Okay. Y coordinate means which can be positive upwards and which can be negative downwards. It can give you the displacement of the point M. What is displacement? I have already talked about displacement. Displacement is distance together with the direction. This is distance together with the direction, which means it has, for the upward direction, it has got positive sign, and for the downward direction, it has got the negative sign. So this is same as the y coordinate, because y coordinate of the point P, which is equal to this displacement OM, is also positive. Y coordinate is also positive upwards, and downwards y coordinate is also negative. So we can replace the displacement OM by y as shown in this rectangle. OM and this y coordinate are equal, but y upon radius 1 is sine theta. Y upon 1 is sine theta. That means y is equal to sine theta. And so the displacement of this point M, which is a to and fro displacement, it goes upwards, then come down, goes downwards, then comes up. This way, this is a to and fro or the oscillatory motion. So it is, its displacement y is given by sine theta. This is what I am telling. Is that clear?
Sir, yes.
Yes. Others?
Sir, yes.
One. Now is it clear?
Sir, yes.
Okay. Gurjot?
Sir, clear.
Urman? Okay. So can I close this screen?
Sir, yes.
Okay. Next, I am taking up what are the values of sine theta for different angles, even greater than 90 degrees. We will make a big table for the values of sine theta. So I am sharing the screen. Some basic values you must be remembering. I will be asking you. What is sine of 30 degree?
Sir, 1/2.
1
1
by
by 2.
1 by 2, which is equal to 0.5, because we want to draw the graph of these sine theta. So we will be needing the values in the decimal form. What is sine 60 degree? Sine 60 degree is
Root 3/2.
root 3 by 2. Now we will use the approximate value of root 3, which is equal to 1.732. Therefore, root 3 divided by 2 is approximately 0.866. But we know we don't need 3 digits. We need only 2 digits. So this is approximately 0.87, we can say, rounding off the third digit. So this is 0.87, and what is sine of 90 degree?
1.
Sir,
1. 1 is to exactly 1, no problem. Now we have to find sine 120 degree. Sine of 120 degree,
Root 3 by 2.
it is equal to sine of 180 degree minus 60 degree. So we use the formula of sine 180 minus theta. It is same as sine theta. So sine of 60 degree. Again root 3 by 2, which is approximately equal to 0.87. Then sine of 150 degree.
1 by 2.
So that is again 1 by 2 because it is sine of 180 degree minus 30. This is equal to sine of 30 degree. That is equal to 1 by 2, which is in the decimal form 0.5. Sine of 180 degree, we have found already. It is
Minus 1.
No. Sine of 180 degree is 0. Exactly equal to 0. Y coordinate is 0 for 180 degree. Right? Just like sine of 0 degree, I have not made the column for 0 degree, I make here. Sine of 0 is 0. Sine of 180 degree is 0 back. Now for sine of 200 degree, sine of 210 degree is equal to sine of 180 degree plus 30 degree. Now we use sine of 180 plus theta and it is minus sine theta. So minus sine 30. So sine 30 is equal to half. So it is minus half. That is minus 0.5. Then we find sine of 240 degree. This is sine of 180 degree plus 60 degree. That is equal
Minus
to
root.
minus sine 60 degree. That is minus root 3 by 2, which is same as minus 0.87. Then sine 270 degree, we have found it equal to minus 1. It is exactly equal to minus 1. Then come to 300 degree. Sine of 300 degree is equal to, we will use the formula we studied today in the morning class, 360 degree minus 60. Sine of 360 minus theta form is minus sine theta. So it is again minus sine 60. So sine 60 is root 3 by 2. It is again minus root 3 by 2. That means minus 0.87. Then sine of 330 degree. This is equal to
Minus
sine
1 by
of
2.
360 degree minus 30 degree. That is equal to sine minus sine 30. And that means minus half, or in decimal form minus 0.5. And finally sine 360 degree, actually it will be 0 back. In maths class tomorrow we can see it, just remember it. So this is the table. I have taken the values of the angle as multiple of 30 degree. It will be easy for drawing the graph now. So anyone, I think this much is clear to all.
Sir, yes.
Uh,
Yes.
so I will proceed to the next screen now. Wait a minute. Closing this screen. Now the next is let me copy these values which we have found. And paste in the next screen. I have done this. Now I am sharing the screen. So I have pasted the table of values from the previous screen. Now I have got ready the angles described on the x-axis like this 90-degree, and I have done three parts. So first part is 30 degrees, second is 60 degree, this way 90-degree, 120, 150, 180, like this up to 360 degree. So on x-axis I have plotted the angle, and on y-axis I have plotted the numbers, because maximum value of sine theta is 1 in the table of values we see, and minimum value is -1. So I have plotted upside maximum value 1, and I have taken its first place decimal parts. 0.5 is shown in the middle. So I have done 5 parts of that. So 0.1, 0.2, 0.3, like this. And in the below side, in the y-axis, downside, I have taken the negative numbers, -0.5, -1, like this. So I am going to plot these values now. So first of all, sine of 0 is 0. This is the point. For sine of 30-degree, I draw a line perpendicular from this 30-degree position. What happens? Yes. And draw sine of 30 degrees 0.5. So I draw a line this from 0.5 position. So this is the position of sine 30-degree value. Then sine of 60-degree is 0.87. So I take 60-degree here, from I draw a vertical line, and then I draw C 0.5 here, 0.6, 0.7, 0.8. 0.8 and 0.9, somewhere in between is 0.87 approximately. So this is that point, giving the value of sine of 60-degree, and sine of 90 is exact 1. So sine of 90 is exact 1. So here this point. Then sine of 120-degree, we have the value 0.87 back. I extend this height line further, and I take a vertical line here, and these meet at this point. This is sine of 120. So I go on like this. Next, I have sine 150-degree at the height of sine 30-degree. I take a vertical line in the position 150. So this is the sine of 150 here. Sine 180 is 0. And now we come to the negative values. Sine of 210-degree is equal to minus 0.5. So I take the vertical line here. This is the value here, sine of 200-degree. Then come next, at sine 240 is same as minus 0.87. So I take the value here, roughly here. So this point is giving the value of sine 240-degree, and sine 270 is exact -1. So I take a line here, take vertical line from here. This is that point. Then again, these values repeat. Sine 300-degree is here. Sine 300-degree is at this level. I take a vertical line at here. So this is the point. Then comes this level back, and so this is the point, and finally sine 360 degree 0. So I can draw the curve, freehand curve. I try to make it as accurate as possible, but so this is, you can understand the graph of, roughly this is the graph of sine theta. Or if we represent the angle by variable x and the value of the sine by y, then we have drawn the graph of y is equal to sine x. So in this form, the displacement of that point M, which is performing the simple harmonic motion, is there. Is that clear?
Sir, yes.
So graphically, it is very clear. First, the point begins from the middle position, neither topmost nor the bottommost. It begins from the middle position or the mean position. It goes up to the highest value 1, then comes down to the mean position, that is 0 level again, but goes further down and goes up to the level -1, and then starts coming up again, and that is level 0 again. Is it clear now from the graph? I think from that picture which defines the simple harmonic motion, it was not very well clear how the point M is moving. But now from the graph, you understand how the point M is moving.
Sir, yes.
So that is the use of maths in other fields. Now this was a topic um, related to simple harmonic motion. Simple harmonic motion is a specific kind of oscillatory motion. A day-to-day life example of oscillatory motion is when wind blows, the leaves of the tree move to and fro. Either they are moving left, then coming back, then move right, then go back, or they can move up, come back, go down, then come back. Okay, you understand leaves, how they vibrate, they oscillate or tremble. So that kind of motion is called oscillatory motion. And simple harmonic motion is a specific kind of this motion, which is given by, in which the displacement of the point or the object is given by sine x. Okay,
Sir, yes.
so this was today's class about. So I am already recording the lesson, and I will be placing the video also. Videos can be used for revising the topic, and for those who are absent, they can also use it. Okay.
Yes, sir.
So I am going to stop the recording, but I have to talk something. First, let me stop the recording.